Hi, so this video is about chapter 10 on energy. As I promised in class, I would give you sort of guideline to the chapter so you can focus on the main points. So the thing I will be discussing in this video will include a broad description of the energy model. Then within this energy model we'll talk about the different forms of energy. That includes kinetic energy, potential energy of the two types, gravitational and elastic. And then we'll make a brief mention of thermal energy, which will be discussed mostly in chapter 11. Then focusing on that, following that, we'll go over the main essential idea, which is the idea of conservation of energy. And we will look at one technique that's used for the representation of this conservation of energy, which is energy bar charts. And then after that, I'll go through a few examples to show you how to use those ideas in solving problems. And as you will see, it's a little different from how we use Newton's laws to find things like position, time, velocity between two different points. This will be a slightly different technique, which will make certain problems much easier to solve than it would have been with Newton's laws.
So once again, here is the rundown of the topics of this video. The first thing we'll go over is the energy model. This will be followed by a brief discussion of kinetic energy. Then we'll look at the two forms of energy. As I said, we'll say a few words about thermal energy. The main point is going to be here on the conservation of energy and the use of energy bar charts. The examples will try to illustrate all of that. Okay. So the energy model is all about, again, systems, just like what we did with the momentum. We will be interested in a system which will be made of multiple parts. The system may interact with the environment, and in this model we'll be interested in what's going on within the system, and then later in chapter 11 we'll be interested in how the system is interacting with the outside world, with its environment. And within the system we will have some forms of energy, such as kinetic energy, which is associated with motion, potential energy, which is associated with position, and then thermal energy, which has basically to do with heat and temperature, and we will talk more about that later. To make things a bit more concrete, here's an example of a system where we have kinetic energy and potential energy. So in this example we're looking at a skater who's on a ramp. For the purpose of this simulation, the ramp is assumed to be frictionless. The system will be the combination of the skater, the ramp, and Earth. The reason for that will maybe appear more obvious a little bit later, but for now that's considered part of the system. So we can represent the kinetic energy of the skater as he goes up and down. As you can see, the value will change depending on whether he's all the way at the bottom, where his kinetic energy will be high, or when he's at the top here, when his kinetic energy will basically be zero. And then his potential energy will depend on his position, depending on how high he is on the ramp. So this would be a good example of a system that will include all the forms of energy that we'll be discussing in this video. Okay, so now let's talk about kinetic energy. So as already indicated before, kinetic energy has to do with motion. Any moving object has some kinetic energy. The mass of the object matters in determining the amount of kinetic energy, but also its speed. The direction doesn't really matter. It can be moving one way or the other. What matters is the speed. So kinetic energy is computed by multiplying the mass times the square of the velocity and taking 1/2 of that. If we take a quick look at the units, then we will see that the kinetic energy will be a combination of kilograms for the mass, meters per second for the velocity. When you put it all together, you get kilograms, meters squared over second squared. And this is the unit we will refer to as joules. So we won't write down the details of kilograms, meters squared, and second squared. We'll just say that we have X many joules depending on the actual number. The potential energy is associated with position. Whether the object is moving or not, it's not relevant. We identify two different types. One is referred to as gravitational potential energy. The other one is referred to as elastic potential energy. And the one thing to keep in mind is that potential energy depends on the chosen reference point, and we'll illustrate that problem a little later when we go into specific examples. So Focusing on gravitational potential energy first. First, notice the label we'll be using for this. It's U with a subscript G for gravitation. So this is the potential energy that's associated with the vertical position, essentially. Depending on how high the object is, its potential energy will increase or decrease. And the formula we'll be using for the calculation of potential energy will be mgy, where m is the mass of the object, g is acceleration due to gravity, and y would be the height above the chosen reference point. I'll come back to this issue of the reference point in a few minutes. So if we take a quick look at the units, we have again the combination of kilograms for the mass, and meters per second squared for g, and meters for y. You put it all together and you end up at the very end of the calculation with kilogram meter squared per second squared, which is the same thing as the one for kinetic energy, and this will be the unit of joules. Let's get to this issue of the reference point for potential energy. In this example, you're looking at a 1 kilogram rock that's 1 meter above the ground, and we have two people trying to calculate the potential energy associated with this rock. On the left, you've got Amber, who's using a coordinate system that counts the ground as the reference point and puts 0 on the ground, and looks at the rock as being 1 meter above the ground. On the right hand side, you've got Bill, whose coordinate system is such that the position of the rock is considered to be 0, and the ground level is counted as -1 meter. So when they do their calculation, Amber and Bill will come up with different numbers. For Amber, the position being 1 meter, you put that into the expression mgy. She comes up with 9.8 joules for the potential energy. Bill, on the other hand, would say, well, the position of the rock is 0, and therefore its potential energy will be equal to 0. Now, that's not a big deal, because eventually, as you will see later in the examples, what really matters when we use potential energy is the change in potential energy and the change in gravitational potential energy. More specifically, in this example, it's very likely that this rock is going to go to the ground, and we'll be looking at the difference between the initial and final potential energy, and that difference will be the same no matter which way you position your reference frame. And so in the end, what will matter is the change and not so much the initial or the final values dependent on the reference frame. So that will not be a big deal, but again, the problems will make this more explicit, as you will see later. Elastic potential energy has to do with springs or rubber bands. That's essentially the same problem, and they store a form of energy that can be transformed into kinetic energy. Spring force we haven't studied yet in great detail, but we will see more of that in the coming weeks. It exerts a force that's non-constant, that changes with the position as the object that's being pushed or pulled by the spring is moving. And because of that, we can't really use our kinematics equation very quickly, so we would have to adapt them, but we will actually do something different here. We'll be using the idea of elastic potential energy. So it turns out that when you look at springs or rubber bands again, the elastic potential energy can be expressed in terms of a number that's referred to as a spring constant. That is a number that is specific to a spring, and I'll illustrate this in a set of slides in a few minutes. So the K comes in, that's the spring constant. The delta S here represents the amount of compression or stretching that the spring has gone through. That would be, again, a distance that can be expressed in meters. The K, the spring constant, is in units of newtons per meter. And so when you combine all those units, one more time you find that the combination works out to be kilograms meters squared per second squared. I didn't write them in the proper order here, but you can see that it's the same combination, and that would be a number of joules, just like all the other energy forms. So energy will always be expressed in joules. Let's talk about the elastic potential energy in the context of a spring. So using this FET simulation, I've got here a bunch of springs, 3 of them, and a few weights that are down here. So I'm going to start by suspending, or actually before I suspend the mass, I'm going to mark the position of the spring. Right now, here's where the 0 is on spring number 1. And I'm going to suspend a 50-gram mass to the spring. it will oscillate a few times, but eventually will stop because we have some friction in this problem. And when the spring stops oscillating, we'll notice that it has stretched 5 centimeters right there when it's holding a 50-gram mass. Now at this point, the spring is exerting a force, upward force, that is balancing the force of the gravity. Gravity is pulling it down, is pulling the weight down, and the spring is pulling up. When we change the mass and we use a 100-gram mass, we come up with, we see the spring stretch a little bit more, and you will see now that it will stretch 10 centimeters instead of 5. And so by doubling the mass of this that's suspended to the spring, we have doubled the extension of the spring. So in the calculation of the potential energy, the value that comes in, the delta S, represents this extension here, which now is 10 centimeters, was 5 centimeters before. And if I were to try the 250 grams, we would get an even greater displacement. Let's see how much we get. By logical reasoning, we should see that if we put 5 times as much, we should get 5 times as much stretching, so that should be about 25 centimeters, and that's exactly what we get right there. I think that's the right number, 21, 22, 23, 24, 25, right there. So the extension of the spring is proportional to the mass that's suspended to the spring. But not all springs are equivalent. So for instance, if I use a different spring, I think spring number 3 is not going to stretch, is actually stretching more this time. Let's see how much we stretch here. That is because the stiffness of the spring can be varied, and so if we make it stiffer, it won't stretch as much. If we make it softer, it will stretch way more than the other one. So that's where the K comes in. So this would be a large value of K. This would be a very low value of K. So you can get a lot of stretching going on here. So this is just a quick illustration of how the potential energy for the spring is computed, and we will see more of that as we go through problems later. As you probably already guessed, thermal energy has something to do with temperature and heat, as illustrated in the picture here. It will turn out to be also connected to kinetic and potential energy when you look at it at a microscopic scale, but we won't be able to talk about that level of description here. We'll just remain at the macroscopic. And so the first thing to know is that an object has more thermal energy when it's hot than when it's cold. There are no specific formula we'll be using for the moment, and as I mentioned earlier, this will be discussed in greater detail in chapter 11, and so at that point we'll see how to figure out the actual amount of thermal energy involved in a given process. Here's a quick illustration of how thermal energy comes about, and so in this simulation we've got a chemistry and a physics textbook that are sitting on top of each other. And we can actually slide the chemistry textbook with respect to the physics textbook, and since there is some friction between the two textbooks, we can expect some result. The thermometer that's over here is recording the current temperature, and so as I slide the chemistry textbook back and forth, you will notice that the thermometer will increase, and that's a reflection of the fact that friction is present, and friction leads to an increase in temperature and therefore in an increase in thermal energy. So this was just a quick illustration of this idea of thermal energy, and as you will see later, it will be mostly connected to friction in most of the problems we'll be studying. Now that we have mentioned the main forms of energy that we will be discussing here, let's go back to the basic energy model. So as you recall, we are interested in what happens within a system. So the system here may include some kinetic energy, some potential energy of either kind, gravitational or elastic, and also some thermal energy, mostly when friction is present. The system may also interact with the outside world, and so there will be energy that may be transferred into the system or out of the system, and that will involve the concept of work that we will be discussing in chapter 11. For the moment, we will assume that this system is isolated so that it doesn't interact with the environment, and so in that situation there will be a first result we can use, and that is that the energy that's within the system cannot be transferred, and so we would have a conservation law, which is illustrated here as the conservation of mechanical energy. What we mean by mechanical energy is a combination of kinetic and potential energy. It doesn't matter if it's gravitational or elastic or both. Within the system there will be a certain amount of kinetic energy and a certain amount of potential energy. When we compare the sum of those energies in the initial state and the sum of those energies within the final state, we will say, in the case of a system that does not interact with the outside world, that the mechanical energy of the system is conserved, that is its initial value is the same as its final value. Later on, if the system does interact with the outside world, we can update this rule, and there will still be some conservation of energy, but there will be more subtleties in the way this energy is conserved, and we will get to those considerations later. Just like in the previous chapters, we will be using some graphical methods to represent the information we are discussing, and one of them here is known as the energy bar charts, and it's best illustrated by discussing a specific example, and I'll show you another more dynamic example in a few minutes. But let's consider here a pebble that's tossed up in the air, and the pebble is initially on the ground, so we have it here with no gravitational potential energy. If we count the ground as a reference level, we count that as 0. To get the pebble to go up, we must give it some speed, therefore some initial kinetic energy. And obviously here the pebble goes up. As it goes up, you know, it will slow down. It will eventually get to a maximum height and then progressively come back down and hit the ground, where its position will again be 0, and it will have the same speed, assuming there's no air resistance here. The speed down here will be the same as the one it was initially. When we try to represent this graphically, we'll use this bar chart, and so the chart here represents the two forms of energy that we have in this problem, kinetic and gravitational potential energy. The bars are meant to represent the amount of energy that we have for each kind. So right here in green we are showing the initial kinetic energy of the pebble right here. It's this much, that's the initial amount. The gravitational potential energy is 0. As the pebble goes up into the air, the kinetic energy will decrease while the gravitational potential energy in blue here is increasing. This particular diagram shows it at the point where both energies are equal. Then eventually, when the pebble reaches a maximum height, its kinetic energy will become equal to 0 because its velocity will be equal to 0. So it will no longer have any kinetic energy, but because kinetic energy plus gravitational potential energy is conserved, we will have a potential energy that will be equal to the amount of kinetic energy that we had to begin with. And then as the pebble comes back down to the ground, the same process reverses itself, and so here again the kinetic energy is increasing and the potential energy is decreasing, and then eventually when the pebble hits the ground, it will have no more potential energy. All its energy will be back in the form of kinetic. If you are interested in the detail, obviously the pebble may bounce back and so on, but we're not discussing this problem here. For the moment, we're just focusing on the basic idea of how to represent the variation of the energy as the pebble goes up and down. We can also look at it one more time more specifically. So the way we'll use these things in problems is we will identify all the energies in the initial state, and we will identify all the energies in the final state. So this bar chart will be, this empty bar chart here will be very helpful in keeping track of all those energies. So in this particular phase here, when the pebble starts from the ground and goes up, it will here have an initial kinetic energy that's some amount, and the gravitational potential energy is 0. When we look at it at the end of this process, let's consider the process to be the move upward, then at that point, at the high point, the kinetic energy is 0 and the gravitational potential energy is all there is, but the amount of gravitational potential energy will be equal to the initial amount of kinetic energy, and that reflects again the idea of conservation of energy that you see here, where the kinetic energy plus gravitational potential energy at the end is equal to the kinetic energy plus potential energy at the beginning of the process. Let's take another look at this energy bar chart in the context of this simulation that we have seen before, where the skater is going up and down the ramp, and the ramp for the moment is assumed to be frictionless, which eliminates the possibility of thermal energy. And so if we wanted to display the kinetic and potential energy of the skater, we can do it right here. We have the option of showing a bar graph, and as you can see, we can see the variation of the kinetic energy in green. When the skater is at the highest point on the ramp, his kinetic energy is all the way down to 0. When he gets to the bottom of the ramp, his kinetic energy will be the highest, and it keeps going back and forth like this. When we look at the potential energy, on the other hand, the potential energy reaches its maximum when he gets to the highest point on the ramp, and then goes down to a minimum when he gets to the lowest point right here. You may notice that the potential energy never goes to 0, and that is because the reference point that's used in this simulation is actually not here, but is on the ground. And we can display that right here with this button. So when the skater is at the lowest point on the ramp, he is still some distance above the ground, and we can see what that distance is. It's about 1.5 meters in this simulation on this scale. We could change that by pulling the ramp down, or by moving the reference point up. So let's do that. Let's change the reference point, and we are going to bring this up, if I can, right here. We'll bring it up to this point. So now when he reaches the lowest point on the ramp, his potential energy will actually go all the way down to 0. And so as he goes back and forth, we can see that his potential and kinetic energy will vary, but the total energy, that's the mechanical energy in this case, that's the one you see on the far right in kind of yellow-green, that is not changing, because as the kinetic and potential energy are changing, their total amount never changes and remains equal to this number. If there was some thermal energy, we can show quickly what's going on here. If we turn on friction, by adding a little bit of friction, not too much, we will see an increase in the thermal energy. That's the one that's shown in red here, and that will happen at the expense of the kinetic energy. He will not be moving as much as before, and progressively will come to a full stop. You'll notice that the total energy remains the same. It's just that now all of the energy has been kind of dissipated in the form of thermal energy. Basically, the ramp and the skate will heat up because of the friction, and that energy will eventually be dissipated into the environment, but that's another issue we won't be discussing here. We're just focusing on the mechanical energy of the system, and that mechanical energy is conserved. It's just that it's taken a different form now. As I said, this will be investigated in more detail in Chapter 11, but since we were on this simulation, I thought I should show it to you anyway, even if we don't do the calculation right now. Let's look at that again in the context of the springs this time. And so I already showed you this particular simulation. This time we're going to display the energy. So let's take a look at the energy that's involved in spring number 1. Right now, of course, there is nothing. Let's grab a mass and suspend it to the spring number 1 and let go. As you can see, there is some variation while the spring is oscillating in the kinetic energy, and that's kind of gone away pretty quickly. The gravitational potential energy is shown here. This is the elastic potential energy. There is a bit of thermal energy because we have some friction, and the total energy of the system is right here. So it's made of a lot of gravitational potential energy in this case, a little bit of elastic potential energy because the spring has been stretched, and also some thermal energy because there is friction as the spring is oscillating back and forth. Let's turn friction all the way down to 0, and just to show you what would happen if there was no friction. And let's suspend some mass, let's say at 100 gram to, well, actually before I do that, I need to display the energy for spring number 3. So right now it says 0. So let's suspend a mass there with no friction. Here's what happens. As you can see, the kinetic energy doesn't die out. It's still there, even though it's been going on for a while. The gravitational potential energy changes up and down as the spring is going up and down. The potential energy changes. The elastic potential energy is also changing because the spring is either compressed or stretched, or not compressed and not stretched, and it keeps going back and forth between all the other options. And so there's always some variation. On the other hand, the total amount of energy, that's the last bar here, that stays the same because the total energy is not affected. But as you can see, without any friction, this could be going on forever, and there's no reason why the spring would ever stop. So when the spring stops oscillating, it's usually because there is quite a bit of friction involved in the process. It could also be the stiffness of the spring. Let's see if we can illustrate this real quick here by increasing the stiffness of spring number 3, and do the same thing. So this time I'm going to suspend this and let it go. So it still oscillates, it's just that the oscillations are not as pronounced as they were before. The spring, the mass doesn't go very low because the spring is pretty stiff. I could maybe make it go way down by suspending something heavier, but that changes the problem. So this was just to illustrate the idea of the bar chart in the context of a spring and elastic potential energy. Same idea, same concept. So in the original plan, at this stage I was going to go into a couple of examples to illustrate most of these ideas, but I realized this video is getting a little longer than expected, and so I'm going to stop it here, and we'll plan on discussing these two examples in a later video, in part 2, which will be posted in the next 24 hours or so on Canvas.